And then
So yeah, I think it's on. So take it away.
Cool.
Yeah.
And then can you close the sort of overlay so I can just see the slide? Awesome. Okay, so hopefully this works, and we'll see if this works in a moment. So hopefully everyone can hear me remotely. If you can't, please hip chat Dimitri, and he'll let me know. At the end, we'll do questions for everyone on the call as well, so we can make sure that everyone is able to ask any questions they want about our testing solution. Unfortunately for people remote, I'm going to primarily be talking this way. At least you can see me, so you can see how animated I am and energetic. Cool. So welcome, everyone. Today is a beautiful morning. We had sunshine in San Francisco, which is great because the last 2 days have been horrendous. Today I came to talk to you about Memsql's scalable testing solution. So the marketing slide is building an infinitely scalable testing solution, but you guys are all engineers, so you know what we're talking about here. We're talking about very scalable software, principles of software that enable scale. So that's what we're going to be focusing on today. Who am I? Carl Sverre, as Dimitri pointed out, and thank you again, Dimitri, for having me here today. I'm really excited. I've been working at Memsql for about 5 years, and I've worked on the Psyduck platform, so the testing platform I'm going to be introducing to you guys today, about half time over those 5 years. When I joined the company, we were only a couple people. At that time, I was pretty much, this was the system that I played with on my nights. You know, everyone knows startups. And during the day, we would sort of use it to test our software. So hopefully you guys enjoy this presentation.
I have to ask.
Oh, so why am I in a leopard suit? So this was our most recent.
Tigger from Winnie the Pooh or Halloween?
This is our most recent energy engineering offsite. It was actually last weekend. We went down to Pismo Beach, San Luis Obispo. It was a really great offsite, and I was dared to wear a animal onesie when we went ATVing, and I did accomplish that dare. So I'm very happy about that. And now this is my profile picture on every piece of social media I have.
Thank you.
I mean, you got to live and learn, right? Okay.
So next week.
Yeah. This is my weekend, guys. All right. So now you guys all trust that I'm a competent person, and we're moving on to why we have to build a scalable solution. So as Dimitri mentioned, Memsql is an in-memory distributed, fast, scalable database. Lots of buzzwords. You know, again, you guys are engineers. I understand. Why is it hard to test a system like Memsql? Well, Memsql is in memory primarily, which means that our tests consume an obscene amount of RAM. That by itself is a problem, but we're also sort of an optimized database. We're designed to be very, very performance intensive. So a lot of our tests run a large number of individual things, individual queries, individual test runs, tests, executions, performance tests, etc. And so what this turns out is that Memsql is really hard to test is another sort of property that I wish was in our marketing slides, but marketing won't let me put it there. So in the meantime, sorry? Yep, so Memsql is written in C++. So very like old school software development, and we just have like a single sort of shippable binary that we test. So a lot of our tests are actually like at the integration test level or the black box level because we sort of ship this like massive blob. We do have obviously unit tests within the code. We compile a second sort of unit test system, but most of our tests are like black box SQL tests. So yeah, so this is Memsql. So properties of our testing system, which are interesting, that we've generated over the time that we've worked at Memsql. We have about 60,000 unique test scripts. A script could contain test transformations, so we do a lot of sort of automated test generation. So we take the entire SQL language spec. We have really intelligent tests that generate permutations of queries, generate random queries. We also do a lot of sort of memory hardening and performance hardening tests. So we do things like injecting seg faults at every possible allocation point in our system. And we sort of loop it continuously until we find a case that fails in a way that involves like a data loss scenario, and that is considered a test failure. So we have a lot of these types of things, and each individual test script can do some or all of these things. So if you think about it, 60,000 unique test scripts can blow up into millions of unique tests very, very quickly without a lot of, we've had some accidental cases in the past where engineers have accidentally submitted like 10 or 100 million tests to the system just by putting the right level of permutation in the system. So we do have a really hard system to test. As I mentioned, our tests tend to consume hours of CPU time or gigabytes of memory, which is one of the reasons why we have an on-premise testing solution. So you guys also have on-premise testing solutions, so there's a lot of corollaries there, and I bet a lot of the reasons why you have on-premise sort of matches over to why we have on-premise. So we'll talk about that a little bit.
On the 60K test, component test or integrated test? What type of
So our tests range the entire sort of spectrum. We have script tests, performance tests, SQL tests, unit tests, every UI tests, everything.
Out of 60K.
Out of that 60K. And I don't have like an exact breakdown, but it is pretty even. We don't have like any one thing overrepresented in our testing system. Yeah. Cool. So moving on, I just pulled some data from the last couple of months. Right now we're running around 825,000 test script executions per week. So again, that's not individual tests, that's script executions which could run millions of tests potentially. So this is sort of our current workload, and those spikes over 1 million tests are usually right around release time when all the engineers are just slamming the system. This system turns out is really hard, and so we needed to build a platform. 5 years ago when we built Psyduck, we started from a sort of environment where the existing distributed, like large-scale distributed system testing frameworks weren't that sort of mature. We tried a couple things. We tried things like OpenStack. We tried things like various like HPC frameworks like Slurm. It ended up being simpler just to write sort of our own system, and so that's what I'll be talking to you about today is why some of the design decisions that went into our testing system. So step one, when you're building any new greenfield product, you got to pick an inspiring name. We chose Psyduck. Anyone who's familiar with Pokemon may know that Psyduck is a Pokemon which is like sort of a telekinetic Pokemon. The reason why we chose it is because it's confused all the time, which is the same expression that engineers have when they're debugging tests. So we wanted to make sure that Psyduck, it sort of represented a lot of things we both love and hate about testing, and so we felt like it was a good avatar for our testing platform. The next thing we do is you have to evolve. So Psyduck has been through quite the evolution. Initially, this was Psyduck. It was 5 desktop machines sitting in someone's room, literally executed just completely manually. It was a complete crazy experience early on in the startup days. We shifted into a closet because that's called a data center in startup land. And initially, it was just a bunch of desktop machines turned on their side. That was our idea of a rack. And this got us pretty far until we outgrew it and put it into an actual cabinet. So Psyduck V3 was still in that closet. When we almost lit that closet on fire due to our AC turning off, and we blew every breaker of the building, we decided to move into a colo facility. So that was sort of the major step up for Psyduck.
You ever walked into your rack in a closet and found snow on it because somebody left the window open?
No, because we did not have nearly enough AC. Yeah, our system ran at like very high temperature thresholds. Good question though. Yeah, we haven't had that problem. We did have the problem where the fire alarm did go off one morning at a Saturday morning, and it was 170 degrees Fahrenheit inside the rack, and it was setting off everything. I managed to get there before the fire marshal got there, so they didn't shut us down. But we did then immediately move to colo because it was getting a little unsafe. So we grew to about 60 dedicated machines in that closet before it was a little bit overwhelming. Hey, person who just joined remotely, can you guys turn off your video, please?
CBC, disable your camera, please. Thank you.
Technology. Alright, so we moved to colo. That was obviously a massive upgrade. We actually found a colo facility in San Francisco with just a couple cabinets, so it was a nice sort of start. Most recently, we're very excited to actually have our own sort of data center space. So we now have space for 20 racks. So we're ready to sort of grow Psyduck to the next generation in our lifetime. So we're a little behind you guys. You guys sound like you have over 700 individual dedicated test machines. We're running at around 200, 250 right now, so about 1/3 of your scale. Yeah, so just some examples. This was very recent. We did this move in the last 2 months, and we're very excited about it. It's been a huge upgrade to Psyduck, and I'll talk about some of the metrics right now. We now have 5,000 hyperthreads, physical hyperthreads in the system. Because we have such a memory-intensive workload, our memory core ratio is actually insane. We have 14 terabytes under management right now. We have 10 gig fiber to every single machine in the cluster, and I think right now our major spine backbone phone is 1.3 or 1.4 terabit. So we have a lot of bandwidth to play with in the cluster. Because we also have a on-disk database architecture, in addition to our end memory, we also consume an immense amount of disk during test execution. And so because of that, we have a lot of local disk available to the cluster. So we have about 800 disks split up between them. So yeah, a system for how many actual systems are in our data center. Cool. So the reason why I'm here today is I really want to talk to you guys about 3 sort of high-level categories that enable infinite scalability in a testing solution, or very scalable testing solutions. The 3 properties that I came up with as things we've learned over the time building Psyduck has been developer friendliness. You need to make it super easy for people to use your system in order to require it to be scalable. If no one's using it, then it's just one machine in the closet and you're all good. Horizontal scalability, we've designed the entire system to be sort of assume that failure is everywhere. And by doing that, we've enabled a really easy ability for us to scale it horizontally as opposed to vertically. And we'll talk a little more about that. And finally, we decided to go on-premise. So for you guys, this is not like a big, exciting, like, oh my God, you're on-premise. It turns out later. What? That's great. That's a good background. All right. Cool. So yeah, so we did do on-premise. We'll talk a little about some design decisions that went into our on-premise decision. So to get started, we're going to talk about developer friendliness. So 3 properties of developer friendliness. Easy. Optimized for latency. That's sort of an interesting one. And debuggable. So if your testing solution doesn't make it easy for developers to actually learn about why things failed, it's sort of a useless testing solution. So we really focus on these areas a lot. To get started, some general language around Psyduck. So Psyduck has runs and tests. And as I said before, tests are nothing but like a script, so you can run really whatever you want, whether it's a unit test suite, whether it's an individual integration test, performance test, stress test, so on. So each individual test can be quite wide-ranging in what it does. A run contains many tests, and our engineers use something called a filter file. Engineers submit runs to Psyduck. Each run is designed by a filter file, and this is sort of an interesting thing. So we designed the entire testing system around these plain text files called filter files, and a filter file contains a bunch of just lines that just are relative paths to either scripts or files inside the current repo. By normalizing around such a simple file format, a lot of engineers have created really, really sophisticated tools to generate interesting testing scenarios. So for example, you can very trivially spider the file system and grab like a ton of tests for particular areas of the engine, but you can also specify arguments to be passed along with these test files. So some of our engineers run permutation tests by just running the same line in a filter file 100,000 times and then specifying like different random seeds. The benefit of doing that, of course, is if you specify the seed in the filter file, if you run it twice, you get the same like in tested environment. And so even though you are generating like random permutation testing, you have 100% control over what ends up happening under the hood. It's really, really great to have simple sort of foundational frameworks like a simple file format basing your entire system on that, because it allows engineers to be very, very creative, which is one of the best things about engineers. Engineers submit tests via this filter file, and as I said before, tests can be a lot of different things. At Memsql, I just highlighted some of our main tests. We actually have a huge number of integration tests because we have so much. A lot of what we do is black box testing of Memsql. So we treat Memsql as a black box, we throw random workloads at it, and we see what happens. Or we inject memory faults or inject disk faults, this kind of stuff. We also have a huge number of unit tests that is compiled into a standalone executable that we can run in parallel inside Psyduck with different sort of initialization parameters. We also have UI tests for some of our UI frameworks, which I'll go into a little bit, and then performance tests and stress tests, obviously. So any questions about like our topology of runs, tests, filter files, that type of stuff? Cool. It should be pretty straightforward, but
so why you are using file instead of using your database?
We also use our database. So the file is just a really nice way for engineers to share tests, like just to share runs. We have a ton of filter files in our repos. that are just like pre-created and they're curated by engineers. We also have filter file generators, which are just programs that will come up with very interesting filter files to test particular cases. We found that just having like a really trivial plain text format allows engineers to be very creative. Under the hood, though, when you submit a filter file, it actually goes into Memsql. So we dogfood ourselves, and we have a single Memsql cluster, which basically contains the entire execution state of Psyduck as a distributed system. And we'll talk a bunch about that because you guys, it's sort of interesting to compare it with your setup, which is using Jenkins, and sort of see where the corollary happens. So yeah, we'll talk about that a little bit more.
Carl, people are telling me that it's a little bit hard to hear you. If you could turn a little bit towards the camera.
I think the mic is up here, is it not?
Yeah, okay. So, anyway, there is...
But I'll just try to be a little bit more clear.
Okay,
yeah. Okay. I'm also talking a little faster about that. I'll slow down. So just on the ease of use thing, we have a binary called Psy, which all of our engineers have on their machines. And Psy has a ton of tools. A lot of the test generation tools that I mentioned are inside of Psy. Any of the engineers can just fork Psy and add other arbitrary test management tools. And the actual Psy binary also contains the test function, which basically allows you to submit filter files. One key property is that we don't return results synchronously in the command line. Whenever you submit tests to Psyduck, they happen asynchronously, just like you guys are pretty used to with submitting pull requests and having Jenkins sort of asynchronously operate on them. We allow our users to do it directly from their command line in their repo with their current working state. So they never need to send any of their current working state to like a pull request or anything like that. I can just go into the repo, make an arbitrary change to engine, and send a test. It's like it's magic. So yeah, it's very important that we make it really easy for developers to make changes, send tests, and not have to go through any heavyweight process around that. Cool. So really quick, one thing that we do that is relevant to that is that whenever you send a test, what we do is we figure out the nearest remote ancestor, so the nearest remote like ref inside of Origin that we can find. And once we find that, we figure out the diff between the current working state and that, and we submit that as a patch. This way, there's no sort of third-party system that is involved in sort of orchestrating patches.
Please mute yourself. We can hear you right now, some of you. Sorry.
Cool. So yeah, so basically we just have this really simple patch-based system, and it works out really, really well to keep things scalable. All right. So optimizing for latency, something that we do is that we round robin based on the actual individuals running tests as opposed to tests or runs. So this is a pretty key thing. It's different than how you guys sort of have it set up. As I understand it, in your environment, you have Jenkins. You have Jenkins, like each Jenkins job, and that Jenkins job is going to coordinate its own usage of compute within your cluster. In our system, we have a pull-based system. So essentially, everyone submits runs to a single overall test queue, and then a scheduler decides on which tests get executed on which machines at what time. We use Memsql to do that. So this entire queue would be stored inside of Memsql, and I'll actually show you guys some of the code that we use to dequeue from a relational table in an atomic way. So basically, our optimization for latency is going to pick tests across the actual individuals and run that way. So it's a little bit a different sort of way of doing it than like everyone just fights for resources. What's up?
Yeah, so when you have run tests, do you run for different versions of Memsql? Because
sure.
So how does one cluster handle, like if split up of the job, let's say Bob is running on a different version versus Carl?
Yeah, so every single test, every single run has a dedicated build asset blob. So essentially when I submit a run, it includes the git patch. That is going to be submitted to our Psyduck builders. The Psyduck builder is going to take that patch, apply it to Memsql source code, and build all of our assets, which is the Memsql D binaries.
Each of the tests build everything.
Each of the runs build everything.
So that blob here, that Bob's blob here is one run.
Yeah, exactly.
So runs are scheduled. Okay.
Yeah, so each run is attached to like essentially a git patch file, right? And then so every single run is going to have a dedicated set of assets that we store inside of our Psyduck environment, and so that way all of the tests for that runs are run against a consistent version of Memsql, which is whatever version is corresponding to that particular patch. Make sense? Sweet. We also actually have the ability to, any test can declare to Psyduck that it wants to have access to other pre-built versions of Memsql, which is really useful for performance tests. So we'll download dynamically like 5 different versions of Memsql and run the exact same test against all 5. And that is all automated by Psyduck. So Cool. So anyway, so just an idea of why we optimize for latency and how we do that. It's a relatively subtle thing, but it really does help with engineers getting results back quickly. So I think overall, inside any test system, something that's probably going to consume the single most amount of time for the company is going to be the amount of time that people spend debugging tests. It's pretty standard. And so we focus a lot of our time on building tools to help this, but also our engineering team builds a lot of tools themselves to help this. Our Psyduck is completely open source within our company, and anyone can contribute to it. And we have a pretty open policy of people accessing and then building on top of Psyduck. So some of the things we do inside Psyduck, which are sort of interesting, a lot of these are pretty obvious. You guys have similar stuff. So we have test output, obviously. This is just literally standard out, standard error from the test script. And so the engineer has a lot of control over what actually shows up here. So it's as useful as the engineer wants to make it. We have a side-core system, so because we are a C++ compiled executable, a lot of our test failures end up showing up as core files. And core files are obnoxious for a couple reasons. One is a test could generate many core files. They could be massive, like massive. If a test consumes 60 gigabytes of RAM, which some of our tests do, the core file by default will be 60 gigabytes. So what we do is we run it through a thing called side-core, which strips out a lot of the data in the core file that we just don't care about and focuses on things like stack traces. And so we're able to get a sort of quick in-memory dump of sort of the entire core file, which a lot of engineers use this primarily to debug what's going on. When that doesn't work, we allow engineers to spin up containers inside of our test infrastructure. So any engineer can go to any test and say request container, and in a couple seconds, they'll get a copy-paste SSH command that will take them directly into a container running inside of the Psyduck environment on the same machine that it failed on, with the same image that it failed with all the same data that like the state of the container at the time of failure.
Okay, how do you do that?
How do I do that? Cool. So it's relatively simple. So every run, as we said, right, a run is a patch. We compile all the assets, and the output artifact of that compilation process is a Docker image. So that's our sort of unit of scalability, our unit of like isolation. That Docker image contains all of the initial states for a test. A test runs, and its entire state is stored within a single test output directory. So all of the things that the test does is we force it goes into one output directory by virtue of that being the only writable location inside the image.
How do you keep people disciplined enough that those things don't end up being a gigabyte each?
It can be. Our storage solution will very happily upload test output artifacts up to 60 gigabytes.
Yeah, but ours is piggy and slow, so.
Yeah, it is actually a problem. Our storage layer for Psyduck is one of the most obnoxious parts of Psyduck in the sense that what it's trying to do is something that's fundamentally very hard. But it does work. So we wrote our own storage system. It is basically a Python key value store that is fronted by Nginx, and it just dumps stuff onto very, very massive RAID volumes. And then allows people to request that later. But yeah, so you're absolutely right. Some people do upload these massive artifacts, which means that whenever they're interacting with the system, it's much slower, and their stuff gets garbage collected real quick. So they have very little time to actually get up. Most of the people, because it gets garbage collected so quickly, and we're very aggressive about being like, well, you didn't get to it quickly enough, most of the people find that what they do, oh, crap, I want my test results to stick around a little longer, so they make it smaller. So we create friction environments to encourage people to do the right thing. So but we don't actually stop people from doing the wrong thing.
Yeah, platform was Linux only? Or?
Everything is Linux, yeah. And Memsql only runs on Linux, so it's real simple. Not only do we only run on Linux, we only run on in Linux 64-bit, like Intel Xeon processors. So it's a really nice environment to be able to test with. We have very consistent. So anyways, so just to answer like the full container thing, we launched this same image that gives you in the initial state. We copy paste the exact same test output state. Thus, now you have the exact state in terms of disk level at the time of execution. And with core files, you're able to reproduce the exact memory state of Memsql at the time. So with those like layers, you're able to reproduce the exact state of the entire system when the test failed. For a C++-based environment, this is just a magical experience. When people drop in this, they drop into GDB and they have like Memsql running in the exact same state of a failure. It just simplifies debugging by order of magnitude. So yeah, it's a relatively simple thing for us to do because of our architecture is built around all of these components, but it ends up being very, very valuable. So when that fails, which it does, sometimes people do really weird stuff, as you said, we allow people to sort of reproduce the entire environment on their machine, which is effectively the same as downloading the entire image and test output, everything locally, and then they can sort of do what they want to do arbitrary debugging. Cool. We also allow people to like manage a lot of stuff for themselves. We actually have an open cancellation policy. Anyone can cancel anything, and people just yell at each other if they do the wrong thing. We found that by letting people sort of do anything, we've really found very little people being like malicious. We've only had to really like give a talking to a couple of people in the company. So our general policy is just anyone does anything and it works out. Not to mention the scales to a company your guys' size, but with us, it works pretty well. We have a team sub 50 engineers, so for us it works out really well. Yeah, so again, filter files are everywhere in the system. Every single command allows you to sort of dump that command as a filter file, which makes it really easy to just open a text editor, strip out some things you don't want, and send it back to Psyduck. Cool, so the last thing that I'll just mention briefly is our UI testing system is actually pretty awesome now because we've partnered with a third party called Testum. Do you guys do a lot of UI testing? You guys obviously have a very, very sophisticated UI, so it must be a lot of UI testing. We use a third party called Testum, which allows you to do they wrap Selenium in a really, really elegant way. I do recommend checking it out. I won't spend too much time on it because they're a full company. You guys can go look at it. But we have actually switched all of the Psyduck UI tests over to Testum. Now we do run them.
Sauce Labs.
Sorry?
You also compared that to Sauce Labs?
Yeah, they actually integrate with Sauce Labs. So they're not a runner. They're essentially a IDE for building Selenium tests in a way that doesn't want to scratch your eyes out and kill yourself.
Right.
So basically they handle, they end up doing a lot of like, instead of taking like a snapshot of like a particular area of the screen and being like, assert that this is correct, they do a lot of machine learning type stuff to basically learn over time based on test failures what is actually correct and what isn't. So they're trying to sort of revolutionize UI testing, and they're doing a really great job. So I recommend checking them out. One innovation we do with Testum is that we run their test runner with a Selenium container inside the environment, which means that our sort of Selenium execution environment automatically scales with the number of UI tests running, as opposed to forwarding all of UI tests to a dedicated Selenium cluster, which is only going to scale as big as your Selenium cluster is. So each UI test actually spins up its own instance of Selenium with its own instance of Chrome and everything. And we found that that actually works really well for our environment. Cool. So I feel like I'm talking very quickly. I'm sorry. I hope everyone else on the remote side can hear me still. We have 2 more seconds to get through, but these are the really juicy sections. I think you guys enjoy this part. So again, developer friendliness, we've found that focusing on that has been really, really key. And everyone at Memsql who uses Psyduck, if you ask them, they'll say they love Psyduck. It works really, really well for them, and I think that that's our metric for success. So we want to talk about horizontal scalability, which I think you guys would be interested in. We achieve this via 3 properties. Parallelism by default. We do not have the ability to run tests serially or in any particular order. By eliminating that from the system from day 0, we made it so that engineers could never do the classic problem of, oh, I wrote a bunch of my tests and now I want to parallelize them and now they all depend on each other. We just never had that in the system. Now, it's sort of automatic that we get this by virtue of the fact that each line of the filter file is a separate execution which is run asynchronously and in parallel, but it is an important thing to just think about. It's like, okay, by parallelism by default, it forces engineers to start writing tests in a slightly different way, which is actually great for like the health of the test system over a long period of time. So we're really happy with that decision. Async and durability is pretty obvious. If you want to build something horizontal, you better make it async and durable. We'll talk about how we do that with Memsql. And the third thing is containerization. So you guys use Docker. You guys are familiar with a lot of the advantages. We'll just briefly talk about some of the things that gives us so everyone's on the same page. So testing of parallelism. One thing we've done is we do not stream results from individual test runs. So a lot of testing systems on the planet, if you're looking at individual tests, you'll be able to see the sort of real-time result of that test, like standard out, whatever it is. We don't do that in Psyduck, and we don't do it explicitly. And the reason is because it forces engineers to make smaller, more incremental tests, because that's how they get feedback faster. And we want that because as the people who run Psyduck, we want a lot of small individual tests that we can round robin so everyone's latency goes down. Right? So all these things fit together in an overall design that makes the experience for both the engineer and the infrastructure engineer much, much better. So it's sort of a small property that we found to be very, very valuable. So this is what it looks like when you are an engineer using Psyduck. Each one of these is a test run, so you think about this as like a patch file, right, which produces an image, which produces a bunch of assets. We have real-time output at the test level, so you can see for each of these runs, you have a bunch of tests that are running, some are passed, some are failed, and engineers can click on those passed and failed badges and immediately see results for all of those things. But for anything that's running, they just have to wait. And so again, it encourages people to make things smaller and more incremental. You can see the filter files. So this online upgrade features, .online upgrade features is the name of the filter file. Most of our filter files are committed, which means that most engineers can just look at this and be like, oh, I want to run those tests as well. They can just go and look at that file. Super, super useful. Shows who's running it. It shows some status about some various things, like which branch they were on. And we do have a priority override system because sometimes it is important at the, like when we're doing releases, to be able to say like this test, like this run has to finish first. So we do have a priority system. Now, if you do set that priority over 11, it sets you back to -10 because we don't trust engineers completely. We just want them to be like relatively nice in the system. So that's sort of a hidden patch that people find out every once in a while and they yell about. And I'm like, we have to do something to prevent you guys from just competing forever. So yeah, so that's sort of the state of how we look at this output of everything. Okay, so async and durability are two key components, and I think that is really relevant to you guys. So you guys have Jenkins, which runs, I'm guessing each like execution of a Jenkins job executes in a container. That container then shards off a bunch of other containers, and because those things are all independent, they all compete for resources within your test architecture, right? Does anyone disagree that that's the state of your system? Pretty much? Okay, cool. So I think this will be very relevant to sort of talk about how we don't do that and like what we've done to make it a little better. So in Psyduck, we use a Memsql table as a durable work queue. So we have a single massive table called tests, and every run inserts all of their tests into that table. That table acts like a work queue, but the advantage is that it's not really a queue per se. It's more like a collection of things that have to happen. And we can use very, very sophisticated SQL queries to automatically sort of check all those conditions that we were interested in. So we have a poll-based system. Every single test execution machine runs a scheduler locally. The scheduler looks at what resources it has available and what tags are attached to it. So for example, certain tests want to run on AVX 512 machines or AVX 256 machines. So we're going to have specific execution tags for those machines, and they're only going to look for tests that match those conditions. So by using a SQL table, we have the ability to inject conditions sort of whenever we want with some arbitrary amount of complexity, which actually is great. SQL is a lock-free, super high-performance system, like in-memory database, which means that SQL tables make amazing asynchronous work queues. We can have thousands and thousands of schedulers all trying to dequeue tests in parallel with zero contention, which is just a magical experience. So they obviously contend, but they don't contend on locks. It's all lock-free, so everyone makes progress, and it sort of resolves and converges to some state that we want. So just to look at some queries, you guys are all programmers, so this could be very interesting. I know the font's not great, but I did want to sort of highlight the way, one way of thinking about a SQL relational table as a durable work queue. So how we do it is we first queue query for tasks. So this is like a very, very cheap query that just says, based on the current like state of the system, what available tasks are there? Give me a couple of those. And that's where we can inject a lot of the complexity around our round-robining stuff. So we can basically say, find me tasks sorted by a particular sorting that includes the round-robining logic. We can also say injecting things like tags for the current machine, particular types of architectures, those type of things. Once we find a couple of tasks, we basically just sit there and just try to dequeue them. So everything in the system sort of converges to a final point. When we dequeue, what we're doing is we're running update queries, and this where predicate is the key. The main part of the where predicate, which is and execution ID is null, or last contact is within some range, allows us to make this thing atomic in the sense that only one of these queries is going to succeed, and every other query is going to fail for a particular row. When the query succeeds, as you can see, we set last on contact to now, we set in our execution idea is we own this row. So it guarantees, because Memsql is atomic, guarantees that only one of these queries is going to claim exactly one row, and every other query will fail and move on to another row. Because these are all running in parallel, we can actually have multiple queries sort of execute in parallel in the entire system. It works out really well. The reason why we include last context is because of the second principle of horizontal scalability, which is assuming everything fails. We want to make sure that if you pull the plug on any machine in Psyduck, no one even notices, except for the infrastructure engineers working on Psyduck. And so the way we do that is by making it so that tasks inherently are dequeuable when they time out. So it's just a property of our queue, is that tasks are only valid so long as they are contacting some recency sort of perspective.
What's your utilization, like what is it, how much of a cluster is utilized at any given point of time?
I mean, for like the Psyduck test execution cluster?
Yeah.
During like a nightly run, like our nightly, which is all of our tests basically, we are running at like 70-something% in utilization. During like daily, it's all over the place. We have hit like close to 90%. It doesn't happen that frequently, mainly because our scheduler is pretty. We take hard dependencies on exact resources. We don't ever do sort of allocate the same resources to multiple tests. Because of that, we tend to get into situations where a test runner has like some empty space that it's not using because the scheduler is just looking for like specific types of tests. So that's where we get a lot of our utilization failure. But that's something we can improve over time. So we're slowly getting better.
So again, the logic is scheduler look at what resources are available in the cluster and then dequeues the task.
What resources are available on an individual node? So every scheduler runs on every test execution host.
So there is a one-to-one relationship between scheduler and node then? Yeah. Oh, okay.
This query on the screen is at the heart of that, as I understand it. I did one using DynamoDB in AWS.
Yeah, same thing,
similar
right?
kind of update where clause.
Yeah, it works out really well. If you have an atomic database that can handle a lot of parallel sort of atomic transactions, then this behavior works for pretty much any database that has that semantic. Memsql just works really, really well because the scale is really high. We have one of our companies.
AWS's goal was for DynamoDB, so you got that.
Exactly.
You're the on-prem equivalent of that cloud-only service.
Exactly. Yeah, and we definitely have people doing that. But one of our customers is Akamai, who we have a great case study with, and they do something similar to this update query for every single bit of data that they receive on their CDN, or that they ship on their CDN on a single Memsql cluster. So we have proven that this thing scales to an insane level, which is a really fun property of a system. So, anyways, sort of interesting track, but this is how we sort of handle parallelizing all of our and using up as much resource as possible. Sweet. So everyone who's worked on infrastructure and distributed systems knows that you should assume failure in every possible case, which will make your life much easier when it actually fails. We like to sit in a world where, like, our hosts, you can just unplug arbitrary things in our data center and no one notices. We actually, with our new data center, have the ability to unplug any single thing in the entire data center, and you will not notice. You can even unplug a couple of them. Even our networking architecture is fully HA. Networking architecture, storage architecture, everything. And the reason why we do that is because we want to make sure that we can maintain and iterate on Psyduck without ever having to stop engineers. Psyduck's become the lifeblood of engineers. Engineers will run tests or runs every couple, maybe every 30 minutes during the course of their day. So they're basically continuously interacting with Psyduck. And because of it, when it goes down or it has latency problems or any type of observable problem, they sort of immediately are going to be on our backs saying what's going on. So that's sort of the premise of assuming failure. So the last thing that goes into horizontal scalability is sort of containerization. We found that containers are a great unit of scalability, and it sounds like you guys are sort of on the same page. The thing I like most about the containers is that engineers control the Docker images, which means that they control the environment the tests execute in, which means that our infrastructure engineers don't have to think about that. At the end of the day, a container contains everything it needs to execute, and you can run it anywhere with a very little minimum amount of sort of interop with the rest of the system. We also sort of find that it provides sufficient isolation. We have played with isolation levels like related to specifying specific Linux capabilities to give to the containers. In general, we do run containers with like a very high level of privilege on the machine because we need our containers to be able to do things like creating network partitions on their virtual interfaces and stuff like that. So because of that, we these interesting scenarios where every once in a while an engineer figures out a way of sort of breaking the sandbox, and then these test runners just crash out. But we found that by giving, again, the sort of principle of Memsql is we give our engineers a little bit more ability to mess with this stuff, and they don't do it because they don't want to break it for them and everyone else. So it works out.
Can you elaborate on performance testing? Because the decision made here was to allocate using node labels some of a significant percentage of our pool to running only a single container in isolation. Do you do something similar, or is there a way of allocating resources without requiring only one container per host?
So how we do it is every single test, every single line of a filter file by default is going to be executed as what we're calling a script test. A script test is allocated 6 cores or 6 hyperthreads, 30 gigs of RAM, or something like that, 20 to 30 gigs of RAM, and then a bunch of disk, right? So that's our sort of default state. Any test can optionally specify in the filter file, I'm a perf test, or I'm a script test, or I'm a stress test, or a SQL test. Depending on what line, what one of those sort of things are picked, it's going to change the resource the schedulers are looking for those tests. When the scheduler decides that it's time to run a perf test, so it sort of goes through like loops of like, I'm a dedicated perf host, I'm not a dedicated perf host type thing. When the scheduler decides I'm dedicated for perf tests, then it's going to look for perf tests only, and it's going to allocate that test automatically as the entire machine. So we do the same thing in terms of performance isolation, just because we can't have perf tests have any neighbors, because we're using like containers as our virtualization layer.
Yeah, I get curious about it because we have these big beefy machines, and not every performance test probably needs 24 cores or however many are on the node.
Yeah. So we control which machines at any one time are sort of considered our perf hosts, and we make sure that they match the expectation of our perf tests in terms of like what they need. Now it turns out that like for us, our perf tests tend to use up like somewhere in the order of like 24 to 32 cores or even more, and potentially like 100 gigabytes of RAM. So we have very beefy perf machines for that purpose. But yeah, so cool. So overall, we feel like horizontal scalability is key.
So the test, additional to resource, also the data. You need a type for a particular test. Probably need to prepare the data for testing. For example, the tables.
So tests bootstrap themselves.
So so those data, each test will allocate those data in the Memsql or is that part of the condition of?
I see. So I think your question, if I understand it, is like, is it the property of Psyduck to correctly set up the environment, or is it the property of the test?
Right. So for example, you have. I understand you
in
have.
relation to data, how do you get data for testing?
Right. That's usually time consuming.
Yep.
Data preparation.
So we have 3 classes of like data preparation. There's the test just generates themselves, depending on how much data it is. There's pre-generated blobs of data that we ship independently of the test that they can request. When they request it, it pulls it over our internal storage layer at 10 gigabit, which tends to be fast enough for most of the tests. And then there's a third case, which is pre-allocated. We pre-populate every single test host when they spin up with a bunch of assets. And some tests depend on those assets. So pre-populated would be like massive blobs of data that we just don't want to move around ever. And those blobs of data they just sit in a standard location on every single host, and we map that into every single test container. So any test container can just grab data out of that blob if they want. Does that answer your question?
Yes. So each test, so you know which type of data preparation it needs. For example, prepared the data.
Yeah, so we don't have like tests declaratively say like I need this thing. The more just the test can just access the thing as it's executing the test. So because these are just arbitrary test scripts, a lot of our tests have to form like grab the data I need or like set up the cluster in the way I want it to be and then run the test on that cluster. We've normalized a lot of the code obviously into like libraries where you can just import. For example, we have a concept called distributed.py, which is a Python library that spins up a Memsql cluster inside the container and sets up like networking interfaces so that it can control things like topologies, network partition, stuff like that. Once you have that little mini cluster, you can then pre-fill it with data depending on if you generate it or if you want to like load data from like a pre-populated source. But we let the tests do that automatically, like themselves. We don't do anything for them.
But that's time consuming. So sometimes the sequential test may save time because the previous test allocated data for the next test. Maybe make that sequential even faster than parallel.
Absolutely.
It depends.
Absolutely, it's true. If a lot of times serialized tests can be overall more performance, like you can get more throughput overall, but your latency per test goes down in certain cases. And now, obviously, you could solve this by like streaming test results per thing. We found that by like with our current system, we don't have like people complaining too much about this problem. People tend to just reduce the amount of stuff that they have to load into their test to be able to test the particular thing they want to test.
How much time usually the loading, memory loading?
I mean, a lot of our tests load in the order of like a couple seconds. So Memsql loads, on like some of our ByCarl Psyduck machines, we can load at 1 million rows per second. So for us, like loading a pretty large amount of data off of disk is not like a performance problem. So we get an advantage of that.
Okay.
Yeah. Cool. So the last area I want to chat about is on-premise. You guys are on-premise as well, so I'm interested to sort of hear if there's any like correlates. Maybe you guys learned something from us. Maybe we learned something from you. The reason why we went on-premise is primarily cost savings. So we did a lot of analysis into how much it would cost to run Psyduck inside of cloud providers or do like bursting type things. And we found that for us at least, it's much cheaper to be on-premise. And we'll talk about why. And the other major areas is noisy neighbors and performance testing. So we already chatted a little bit about perf testing. Having dedicated machines that you control the entire down to the bare metal is very, very key when you're doing large-scale performance testing. And then for noisy neighbors, we want to know everything running inside the environment. Anything that is not is considered like, if there's something that's running that we can't actually look at via our metric stack, it means that we're going to have weird unknowns and people are going to complain, and it'll just create a bad experience. So those are our primary reasons why we're on-premise. We did a bunch of analysis during this most recent data center move. We actually tried to determine what it would cost to take our old co-location space. So like we had 8 cabinets with like 160 machines total at that time. We decided, okay, what would it take to take that workload and put it in either AWS or GCP? We priced it out, and conservatively, we hit 3x to 4x, including the expense of hiring engineers to work on the platform on-premise. That's because we need a lot of dedicated fat machines, because Memsql, like a single test needs to have 20, 30, 40 gigs of RAM. Once you're at that model, AWS and GCP really starts to hurt. If you're able to run your tests in like a bunch of super tiny VMs and you're able to scale out that way, and you're able to take advantage of like spot instances and that type of stuff, you can get the price down a lot. But for our workload, it's just not feasible.
I would love to be able to make that case here because we run up against that. Well, it's CapEx, and we don't want to spend more on the data center. And
it's a hard case.
Those are the numbers that I feel in my gut, but I don't see them.
Yeah, if you want, we can separately have a meeting, and I'd be more happy to show you our actual analysis.
I know what we spend on AWS, but I don't really know what we spend on the data center.
Yeah, okay. So we did like a very, very thorough, very deep breakdown of the entire stack, and this was our outcome, which was very interesting, actually, very eye-opening how expensive it was. Yeah.
I used to run data centers, is why I see that.
You have like an intuitive idea.
Yeah.
So the second thing that we found is that noisy neighbors is a big problem in cloud providers. We run Memsql workloads. A lot of our customers actually run Memsql in production inside cloud providers. And we notice these weird performance variances very intensely because Memsql is such a performance-sensitive database. If someone else is on the machine and they're just slamming CPU caches, they're slamming I/O or whatever they're doing, we'll see that in our perf. And for testing, it's very annoying because we have so many integration tests, and we have so many tests that operate Memsql as a black box. Those tests inherently take a sort of a dependency on multiple Memsql nodes running co-located with the test and particular latencies between those nodes. So because of that, we have a system where we notice noisy neighbors immediately, and it's very frustrating. So dedicated machines allow us to sort of eliminate that problem and know exactly what's running, and we can track down our own noisy neighbors, like tests that are just not playing very well, and get them either to be fixed or talk to the engineer and figure out a solution. So that's sort of the plan with our platform. And the last thing to talk about is sort of performance testing. And so we obviously addressed this a little bit, but we reserve entire machines for performance testing, and we make sure that when we're running the same perf test against different versions of Memsql, it runs on the exact same host, with the exact same environment, with the exact same set of processes running. We don't want to ever have a situation where people make some conclusion from a performance test, and then that conclusion is based on invalid data because there was something else running on the machine and they made some invalid conclusion. One thing we do is we continuously will run perf tests in nightlies as well. So even without engineers actually actively looking at those outputs, and we do that for two reasons. One is just have a lot of data in the system, so you can do long scale performance analysis of commits over a long period of time. We also do it to verify that our performance system is not changing in a massive way. So we track the overall variance over time at a nightly level, and if we're seeing the same tests changing a huge amount over maybe a week, either someone's committed something that's bad, or performance tests are now running in a particularly different environment. Maybe something else is running on the machine, maybe our perf test system is doing weird, or something we've actually detected before by doing this is the machine has suffered some minor problem, like its disks are operating 10% slower. And we can quickly detect that by doing it this way to get those machines out of the fleet before they cause people to make coding decisions based on those changes. So yeah, that's really it. Those are the three properties of developing a infinitely scalable testing solution in Memsql. And at this point, it's really just what's up to you guys, in terms of questions. I mean, I've already asked some really good questions on the way, but I think that the best thing I can do to provide you guys the greatest context is be willing to talk about anything in the last 5 years that we've worked on. So at this point, it's open to questions, and thank you so much for your time. I hope that we didn't go over time too much. I know we started a little bit late, but yeah, at this point, it's up to you guys. And also, if you're remote, feel free to unmute and ask questions. But yeah, anyone here have?
You can even unmute your video if you'd like.
You can even unmute your video. Yeah, and sorry I've been on my back screen to you guys the whole time, but we need to move the camera over there. Any questions?
So your site system basically is kind of slower, right? Uninstalled Python node, you have a site running, service running, then constantly query the database to get a new test.
Yep.
Then run.
Yep, that's exactly right. So we have a pull-based system. The schedulers run locally on every machine. They monitor the machine in terms of what's running on the machine, the status of those things, making sure that there's nothing breaking terribly. And then when there is space for new things, then it goes and queries. So it's quite smart piece of technology in the sense that it does the minimum amount of work necessary to be able to make progress. But yeah, each machine is completely independent, and you can just kill machines arbitrarily, and those tests will immediately re-queue to other machines to continue execution. Or I guess not continue, restart.
So intuitively, if you have the system that developers love to use, they're going to be testing a lot more. You'd expect the software to get better quality over time. Have you tried to ever quantify that, make a plot of number of bugs over time or incidents over time, that kind of thing?
I would love to show you some of the stuff we've done with that, but yeah, we've absolutely looked at Psyduck metrics over time. So some of the interesting things is that we have stored inside the Memsql cluster running Psyduck every single test result and failure and outcome for the last 5.5 years that Memsql has been around in one database. Because of that, we can do very, very long-term analysis. So some of the things we've done is mostly around performance testing, is we're actually debugging not only the underlying machine hardware, whether or not it's changing over time, but also whether or not our code is sufficiently changing in performance over time. So a lot of that is done automatically, but also we've done for releases, a lot of times we'll pull data just to be able to do analysis around, okay, between 5.0 and 6.0 of Memsql, what were the major changes? Were particular tests failing or not? Another thing that Psyduck does that I didn't talk about is that we have a flakiness detector. So Psyduck will automatically try to identify tests that are low quality, and it does that by looking at sort of historical execution of that test, whether or not it flakes all the time, whether it's just started flaking, whether or not it's just started failing or whatever, which we found to be very, very useful in getting the signals to developers to help them learn. Cool. Any other questions?
Can I have one?
Yeah, of course.
Go ahead.
My question is, can I have one? Because it looks awesome.
Oh, you mean, can you have a Psyduck?
Yeah.
I thought you meant you could have a question. Yeah. Well, no. Unfortunately, yeah, the Psyduck code is not exactly it's one of those like internal tool projects that's like works really well for us, but it would be really entertaining to try to get it running anywhere else. But what I'm hoping is that really what the magic of Psyduck is these basic ideas that I presented, right? It's not so much the code, it's not so much the architecture. To be honest, Psyduck is not that complex of a piece of system. Like, there's not a lot that goes into what Psyduck is. What is magical about Psyduck is the particular design decisions that we made over the last 5 years that has made a system that our developers truly love to use and are able to make a lot of progress really quickly. And I think that is by far the most valuable part of Psyduck. So hopefully I basically just gave it to you. It's right there. It's just in slides. You just have to write the code.
Slideware.
Yeah.
To that end, what's standing out in my mind is we're nowhere near able to roll anything like that out at our company, partly because we're not quite tenfold the scale in terms of engineering team, but also herding the cats, getting people to agree on anything becomes much more difficult when you've already got a legacy of arguably some fairly broken business processes. So I'm trying to steer us towards something new. We've got some support from management, depending on which team it is. Maybe not, maybe yes. Trying to frame this into a question.
How do I do it?
Well, we've got, say, Jenkins file. Finally, Jenkins has made the leap from UI configuration to code-based configuration. One of the pitfalls with that, though, is that it's this powerful tool for developers to do anything they want, however they want. And there are 15 different ways of doing any given thing in Jenkins because of its long legacy. It looks to me like you've got one major way to do any given thing in your system, and the developers rally around that. So how did you get to that point? Was it just natural, or did you wrestle with this too?
Yeah, I think in software engineering, there's sort of two ways to make like massive product changes in any company, right? One way is from day zero, you just said, this is the way we're doing it, and you were lucky enough to create a system that everyone like rallies around, and you made enough initial design decisions that you didn't like hate yourself in 5 years. That was the way we did Psyduck. So it's more luck than anything else.
Okay.
The other way, obviously, is like Skunkworks. Like, you just build a better system, and then everyone just starts using it because it's better. The big problem with you guys is that you're huge compared to us, which means that you guys building a better system is a huge monetary investment. Whereas for us to build a better system, like many times over the years, Psyduck has been improved by random engineers who are annoyed by random stuff. And the way that they did that was they literally just took the Psyduck code, changed it, ran it locally, verified it works. There's not really that many tests for Psyduck. It's mostly just tested by virtue of just being in use constantly by everyone. And they basically just submitted it to the test infrastructure team, which for a really long time was just me. And I would go like, yeah, that looks pretty cool, and then I'd ship it. And really didn't ask a lot of questions. It's not scalable, absolutely. At a certain point, that starts to break down, but we've managed to keep it like a very fluid sort of system. Yeah, that's a terrible answer. But it's best I got.
Yeah, I get it.
So when did you guys start using Docker?
Oh, we started using Docker in Docker Alpha. Yeah.
That's like .cloud or something?
Yeah, when it was still called .cloud. Like when the company was still .cloud. I went over and met Solomon Hikes when he was just starting to play around with it. And I was immediately like, this is the future of orchestration. It makes perfect sense. And we started using Docker almost the next like month. And because I ran Psyduck at the time, I literally just switched us to Docker and didn't really ask a lot of questions.
So you built your own scheduling stuff?
Yep. We built our own
So
scheduler.
you don't use any orchestration?
We built all of our orchestration before there was
anything. You just built your own thing, right?
Yeah, we built our own thing before there was anything.
Because there was nothing there at that time.
Yeah.
Not your Docker Swarm.
How is it compared to existing?
It's very similar. I would say it's similar to. We have a pull-based architecture. Like a lot of the containerized platforms are now push-based architecture, like Kubernetes, for example. Like Kubelet's receive, like you should run this thing. And Kubernetes is a great system because it's so decoupled. Like nothing really has to exist with anything else. If I was going to do it today, I would probably use Kubernetes. The biggest problem with Kubernetes is it's not designed around the concept of a very large execution queue with relatively few numbers of actual execution nodes. Kubernetes takes the approach that if it cannot schedule something, it just rejects you. There's no like queuing, right? So the biggest problem with Kubernetes would be that we'd have to wrap Kubernetes with some type of queuing logic. Something we are also looking at is potentially switching over to like using Slurm with our own executor. Slurm is like a classic like HPC like large-scale distributed computing framework. Slurm scheduler supports a lot of the basic concepts that we use in Psyduck, but just done by people like 30 years ago who actually understood distributed systems. Not that we don't, but you know, there's some advantage in using systems that have been battle tested, which is really nice. But at the time when we wrote Psyduck, it was much faster just to build like a very simple pool-based scheduler. And then of course we have Memsql, so we sort of had free like compute scalability for our actual testing system because Memsql scales to a point that's so much larger than the entire Psyduck workload. Right, like a single Memsql node can handle the entire query execution environment of Psyduck. The rendering of all the pages, the entire test queue system, everything. It's all in one node. And that's just because our software is very, very fast. So we do have the advantage there.
Could you talk about how the output from Psyduck ties in with your CI/CD process and whatever business process you have around making release or shipping decisions?
Yeah, absolutely. So Memsql is a code review culture. It sounds like you guys have a pretty good code review culture as well. So every single change that goes into Memsql, any branch, any piece of code has to be code reviewed. We use Fabricator, which is a product from Facebook, to do all of our code review. When you send a code review, we expect our engineers to attach Psyduck tests. So we've altered Fabricator to basically allow you to sort of say, here's like 5 Psyduck test runs that I ran, and they're either currently running or they were running. We will automatically attach test results from Psyduck into Grizzly via a little bot that just continually like tries to correlate Psyduck with Grizzly. But because of how Psyduck is written, a single pull request might have like 20 or 30 runs attached to it. So it's not just like this is the one thing that verifies this entire pull request. It's just here's a history of test runs I ran, and then like the last 5 all passed, and you look at what filter files they ran, and you're like, okay, great. Like this seems like it works. Once people sufficiently agree that a particular code review should be shipped, we merge into master, and every hour we submit what is called a .Psyduck, which basically runs our sort of verification test suite, which is about 20,000 tests that verify that the current state of master is sufficiently safe to continue to make progress. If you have a test failure in either .Psyduck or in the nightly test run, which happens every day, you are put into bug jail, at which point you must complete whatever issues you've created by the next nightly. So you have like 1 day to fix problems. Now, obviously, like we're flexible with people having like doctors and stuff like that, but in general, it's a pretty important thing that we keep master at a very, very high level of stability. Our release process goes through a couple weeks of verifying that nightly is stable. So once we start the release process, we switch the entire team into you're doing nothing but fixing bugs, and we keep on going until nightly is green. When nightly is green, that's when we decide the engine's stable. We have a lot of history of building up our nightly that we trust it a lot, and to this date, we've never had a data loss scenario with any customer. So we're pretty happy with our track record. So yeah, I think, does that answer your question, or do you want me to go into more detail into any particular area?
No, that was absolutely perfect. My follow-on is for the failures, do you guys prefer to let them fail and keep things red, or for flaky tests, do you put them into kind of an ignore mode?
Great question. So we keep track of all of our failures because we want to make sure we have enough data to make decisions. But what we do with flaky tests specifically is we automatically retry them when we detect that they're probably flaky. We track both the failed attempts so people can go debug the flaky test, but then we also like say, oh, we retried it 5 times and then now it's green. There are configurable parameters to control all of this type of behavior, but the default is most people just stick with them. As for failures that we don't detect as flaky, we treat them as like, this is a bug, and we have a system in Psyduck that will automatically file tasks against engineers. So we track like, usually we'll file tasks against some of our engineering managers, and they'll end up auditing where the task ends up getting filed against, like who ends up having to do it. But we do have, during the course of a week, we'll file 100 to 200 test failure tasks. Some of them are closed due to, the engineers saying this was a flaky thing, we'll mark it as flaky, we'll get to it later. Some of them get actually filed as bugs, and it works out pretty well. We have a good iteration sort of speed with that system.
Very cool. Thank you.
Yeah, sweet. Any other questions? I think.
Yeah, I have a question. How do you guys log stuff, and where do you see all those?
So for test outputs, right? So we track. So a test output is nothing but like a script output. So basically, the idea of a test is you have some test script which has standard out. All of that is tracked as the primary output for the test, and that's just uploaded, and then you can just view it online. But the test also generates this test output directory I mentioned earlier, which is the only writable location inside the container. That entire directory is packaged up and uploaded to Psyduck. So we spider through it. We do a couple of heuristic checks. So we check for core files. We run scikor on those. We check for other test outputs. Like, for example, we have like whitelisted file names that we look for, and we'll grab those and put them directly in the UI so that you can get access to, for example, like Memsql trace logs directly in the UI without having to download the test output folder. We grab core files. We do analysis on those. We remove a huge amount of data from core files because there's so much data that ends up getting in our memory. Like, for example, we have full control over our memory layouts. We don't leverage the kernel too much, which means that we end up pre-allocating like a huge amount of data, which just ends up being like zero or random noise. So we remove all that, for example. So basically, long story short is a test output contains the standard out of the actual test script, this massive blob of random stuff, some of which is then pulled and put also in the UI directly.
So how is it indexed, and where do you store it? Like an Artifactory type of repo, or what? Because the problem that I am trying to solve is, right now anyway, is that Jenkins creates these temporary artifacts which we're not yet sending to a more permanent managed repo. So they expire within a week or two, and then somebody picks up a bug report 2 weeks later, and the console output, the test output is gone.
That's a really good question.
Let alone being able to press a button and say, give me the container that's got
Yeah, so that's a really good question. So we have a very aggressive GC policy on our test artifact system because, as I said before, we generate an immense amount of data in our tests. But obviously, a really key thing is like if I file a bug on some test, like that better be there when I go and look at the bug, right? So how we solve that is that we have a spider that spiders our entirety of Jira every hour and finds all of the tasks that link to Psyduck resources, and then it pins all of those files in our file systems, so they never get GC'd. Which means we do have this slowly accumulated buffer of we just have to keep this data around, which we periodically manually GC by just saying we're done with all these.
Still scriptable because you can have it query the Jira.
You can find all the final finished tasks and clean those. Yeah.
So I think ultimately it's all about the culture, right? So they have 50 engineers or so. If there is some problem, like Carl just described, the engineer just sits down, writes a tool really fast. And here you go, the problem is solved. Yeah. So it's all about engineering culture and how to cultivate it. That's my opinion.
Yeah, and all of the things I've described, every single part of this talk, except for some of the core initials conditions that we've created, for example, the fact that we don't stream test result output, that was something we decided really early on. All of these things were created by random engineers. I didn't write all of this code. I just am a moderator.
I'll take on one more 800-pound gorilla here. What you just said made me think, what's broken about Agile in this company? Because we don't have engineers, like what you're talking about, saying, hey, I'll go up and do this thing because it'll help productivity. Instead, we have top-down decision-making that says, here's the backlog, here's what we're going to ship. Let's focus all of our engineering resources, including the infra team resources that I'm part of, on deliverables that are outward facing. And there's virtually no ability for us to say, wait a minute, we want 20% time to fix our own shit.
I think you just hit the nail on the head.
Yeah, no, I think that's key. So at Memsql, we do not do an agile thing at all. Our CEO is Nikita. If you ever meet him, you'll know why. We definitely take with a policy where we hire people who are go-getters. We want to hire people who go do this stuff because they love it, and they fight back if they don't get that ability. So a lot of our engineers do spend 20% of their time, whether or not we like it, on improving the environment. We've had a lot of tools that have been built internally that we've ended up shipping to customers because they're just so good. People have just done a really good job. So it is a culture thing, absolutely. And then the second thing is that we have our shipping process is based on our VP of engineering, or senior VP Adam, who worked at Microsoft, and it's very old school, very waterfall based development, but it allows us to allocate this type of time, and so we like it.
Have you guys thought about selling this?
Actually, we have. Nikita's thought about it a couple times.
I'm having a dinner with Nikita tonight, so we'll discuss this.
You have access to the pocketbook here.
Pay for the blood I put into it.
Even if it's only 50 lines of code, right?
No, yeah, we are really happy with Psyduck, and we do consider it like one of our secret superpowers that if we ever did sell it, it would be a really entertaining product for sure. I think it could be interesting.
Yeah. That's more ammunition for talking about changes, because we're in this slow-moving reorg of our management. So I don't think our agile practice is a sacred cow. I think we can take it on.
No, that's awesome. I mean, it's all about finding those things. I think the key for me is I want to always work at a company where I can go and do this type of stuff. Like when I took over Psyduck, no one told me to take over Psyduck. Right? I just saw a bunch of pile of machines. No one was taking care of it. I just started taking care of it. And then now I own Psyduck, which is a terrible decision. Yeah, so that it's one of those things. Any other questions on the remote side? Cool. Well, I hope that this was helpful. My deepest desire is that we can get more Psyduck-like technologies in more companies, because I think that it's been a huge help to us. It's accelerated our shipping ability. Everyone in Memsql truly loves Psyduck, and we enjoy playing with it. So hopefully you guys learned something about it.
Yeah. Thank you very much, Carl. Thank you, everyone.
Thanks, everyone remotely. Hopefully it was not too hard to hear.
Have a good day.
Yeah.
Thanks, Carl. It was great.
Thank you.
Thank you so much. Cheers, guys.
Bye-bye.
Cool. And then the recording, hopefully.
Yeah.
To pause, and then you have to open a service now to get the link.
So I hit stop though, right?